Okay, so remember what we did yesterday was we discussed how to build a variety of fault-tolerant gadgets. So I defined for you fault-tolerant. So in these pictures I switched to red, which may be slightly more clear as a color for the ideal qubits. And remember, the thick white lines are the physical code blocks. So we have these definitions for different kind of gadgets. We've seen, at least for the 7-qubit code, we saw how to do the Clifford group transversally. That's a fault-tolerant gadget. We saw how to do state preparation and measurement and error correction for the 7-qubit code and sort of for more or less for more general CSS codes. But what we're still missing is the universal set of gates. So I started to show that to you in the form of magic state injection. So if we can make those magic states, you remember, and the ones that I was talking about before. So here's the magic state injection procedure. Remember, so we have a Bell measurement here, and we have some state here, which is our magic state. And we have the two classical bits that tell us to do here a Clifford group element. And so the last missing step then is how so if we do all of this at the logical level, where we at the encoded level, where we have an encoded block here, we do the encoded Bell measurement, which involves Clifford group gates and Pauli measurements, and we do the encoded Clifford group gate. Then the only step that's missing in order to get a universal set of gates is to figure out how to make this magic state in an encoded state, right? We need to do that in a fault-tolerant way. So that's what I want to talk about first. And there's a couple of different techniques for doing this, but probably the dominant one that people are using in analyses today is what's called magic state distillation. So you remember that when I was telling you how to make logical zero states as fault-tolerant state preparation, I said we'll make a couple of them and we'll compare them against each other to see if there's errors, right? And so either one that we made by itself could reasonably be totally wrong with just a single faulty location. But two of them, it's unlikely that both of them are wrong. That would require two faults. And so by comparing them against each other, we can detect when one of them has gone wrong. And magic state distillation works on the same principle. We're going to create a bunch of these encoded magic states, each of them created in a non-fault tolerant way, so that we can't really rely on them being correct. But then we're going to compare them against each other. And by comparing, we can identify that there's an error, or in some cases, where the error is. And then we can use the remaining ones to plug into our computation and do gates. Okay, so the cost of this is just like before we had to make two states, but even if they were both right, we only got one out. So in this case, it's the same problem that we're starting with many of them, and we're ending up with only one. Or you could do it many times and end up with multiple ones. So that's kind of the place where this term distillation comes from. You have kind of low quality magic states, and you're putting them all together and boiling them using the distillation procedure. And then what comes off is a smaller number of purified, more reliable magic states. So to talk about magic state distillation, usually we again forget about the fault-tolerant protocol per se, and just kind of boil it, well, maybe a bad use of terms given I was just talking about distillation, but and kind of reduce it to the essential components that we already know how to do. So what do we already know how to do? We already know how to do Clifford group gates. So we're going to assume that we can do perfect Clifford gates. And Pauli measurement. Okay? Maybe I don't need this. Make it a colon. Okay. And so so we're going to forget about the error correcting codes we've been using so far for the moment and focus on a model where we know how to do this, but we have imperfect non-Clifford group gates. And these imperfect non-Clifford group gates would enable us to make this magic state I tensor U 0, 0 plus 1, 1, but it would be noisy. Okay? And our goal is to make a better magic state than we could make using just a single one of these imperfect non-Clifford group gates. Okay? So is this model clear to everybody? So for the moment, I want you to forget that it's part of a fault-tolerant procedure. Okay? I'm just focused on this one goal, how to make better non-Clifford group gates or non-Clifford group states, non-stabilizer states. Okay? And the reason I keep hammering that I want you to forget about the fault-tolerant protocol is because the way we're going to do this is to use a quantum error correcting code. But it's a different quantum error correcting code than the one we're using in the fault-tolerant protocol. Okay? So that's why I want you to not think about that other protocol. Just we're going to focus on this error correcting code. And in particular, we're going to use 15 qubit for this particular protocol that I'm going to show you. We're going to use a 15 qubit code. It's actually a stabilizer code, a 15-1-3 code. So it can correct an arbitrary single qubit error or detect 2 qubit errors. It encodes 1 qubit in 15. And this 15 qubit code, I want to pick it because it has a very special property, which kind of came up in some of the discussion earlier, which is that the transversal, it has a non-Clifford group transversal gate. So in particular, if you do, I guess, R minus pi over 8 tensor 15, that implements the logical pi over 8. Or vice versa. Or maybe it's easier vice versa. Let's do it that way. Okay, so this is very much analogous to the 7 qubit code, where the pi over 4 rotation, you did it on every qubit, and you got the minus pi over 4 rotation, the logical minus pi over 4 rotation. And there's a good reason for that, because these codes are pretty similar. So the 7 qubit, well, the 7 qubit code is based on is a CSS code. This is also a CSS code. And it's based on a classical code, and the logical 0 for the 7 qubit code was a superposition over code words that had weight 0 mod 4. And the logical 1, it turns out, is a superposition of things that are weight 3 mod 4. And so if you apply the r pi over 4 rotation, you get a factor of I for each 1 in the state. And so things that have 0 mod 4 give you plus 1, and things that have 3 mod 4 give you I cubed, which is minus I. Right? So that's minus the gate, or the dagger of the gate. And similarly, this thing has code words, is classical codes, where the logical 0 is a superposition of things that are weight 0 mod 8, and the logical 1 is a superposition of things that are weight 7 mod 8. Okay? So we can do it for not I, but for the square root of I phase. Okay, and so once we have this code, so remember, let me just write down what that pi over 8 gate is. So once we have that code, here's the way the magic distillation procedure works. So we're going to take, forget about magic states for the moment. Suppose we make this 15-qubit code, okay, and we're gonna use it to encode the logical state. We're going to have 2 blocks, and we're going to encode the logical state. That's the magic state we want to make. Sorry, that's the logical state 0, 0 plus 1, 1. Okay? So we're making a logical Bell state. This is fine. This is stuff we can do with Clifford group gates. Why? Because this is a stabilizer code, so we can encode it with Clifford gates. And this is a stabilizer state, so we can make it with Clifford group gates. Okay? So we can make this, this logical Bell state using just stabilizer states, using just Clifford group operations. Here, let me make some distinction between the 2 code blocks here. Okay, so once we've done this, we want to convert it somehow to the magic state, right? And so one way to do this is using this transversal pi over 8 gate. So suppose we do r pi over 8 on each of these, each qubit of the physical qubit in the second block of the code, right? Now, of course, we don't know how to do this perfectly. But if we did do it perfectly, then we would get almost what we wanted. We would get I tensor r pi over 8 dagger times 0, 0 plus 1, 1. Okay? But that's basically the same, because it differs from the correct one by simply a Clifford group operation. So if you then do I guess we have to do r pi over 4 dagger here. Then we'll get back to exactly what we wanted. Again, assuming no errors. Okay? Yeah?
So in this code encoding, the r pi over 4 gate doesn't have a transversal implementation.
Well, it does. And you can immediately see that it does, because if you do this twice, right, what are you doing? You're doing r pi over 4 tensor 15. And what do you get? We get r pi over 8 dagger times itself, which is r pi over 4 dagger.
So in this case, which of the gates do not have a transversal?
The Hadamard. The Hadamard is not. Because for the 7-qubit code, both the 2 codes were the same. In this case, they're not. Right? So that's what you're giving up here. And of course, you have C naught because it's a CSS code. Okay. So we have the transversal pi over 4, so we can do that. And that's just Clifford group gates. So these are OK. This part was OK. And this part here is the part that we're worried about, because there will be errors in that, because the non-Clifford group gates are imperfect. OK? Is everyone with me so far? OK. So now let's think about what happens when there's errors. Let's say one of these gates goes bad. Okay? We'll say the error rate here is p. And P is maybe not super low, but it's not super high either. So let's say it's 10%, something like that. Or less, 5%, 1%, something like that. But it's going to be higher than what we get for the Clifford group gates, which we're assuming are perfect. So what happens then? Well, when P is small but not too small, there's a pretty good chance that one of these will go wrong, but it's not too likely that two of them will go wrong. And actually, in this particular case, it's, well, OK. Let's assume that one of them goes wrong. OK? So one of them goes wrong. And so we might have an error here, say. Here, maybe I can use a... And so that means that the state we get out will have an error on this qubit. The other qubits will be fine, though. OK? And because we're only doing transversal gates, this error is not going to propagate anywhere else. So that means that if we do error correction, here, that we'll be able to detect this error. And because it's a distance 3 code, we can even identify where it is and correct it. OK? And so that means that if there's one error, we get the right state. Well, we sort of get the right state. So the next thing I want to do is I want to decode this. And because we've gotten rid of the errors, when we decode, we get exactly the magic state. OK, and so if if there's one error, we get the correct state. Now, the way I've said it, we're gonna correct this so that if there's two errors, then we might not get the correct state, right? Because our error correction procedure might fail. This is only distance 3 code. It might not correct two errors. But the chance of this is O of P squared. OK? It's going to be like roughly 15 choose 2 times P squared for the various places that you can get two errors. OK? So the point is that when P is smallish, we've made it much smaller. Right? Which is just what happened with error correcting codes in general, right? We're taking small errors and making them even smaller. So let's see. So there's a couple more steps to fill in here. So first of all, this is saying we're going to take the ability to perform imperfect gates and turn them into a slightly better magic, in somewhat better magic state, right? But what we're really interested in is in magic state distillation is taking mediocre magic states and turning them into better magic states. But remember, we know how to use a magic state to perform the pi/8 gate. So suppose instead of the ability to perform non-Clifford group gates, we just have a supply of imperfect magic states, right, that have error with probability p. And each one of them can be used to perform a pi/8 gate using this circuit. Now, if the state is good, if it doesn't have any errors in it, we'll get exactly the pi/8 gate out. But if the state is wrong, then we might get something else. So, the possibility of an error in the magic state corresponds exactly to the possibility of a fault in the pi/8 gate. Okay? So this is then a magic state distillation procedure. If we implement each of these via magic state injection, we can start with 15 noisy magic states with error probability p each, and get out one better magic state. with error probability O of p squared. Okay? So does everyone understand that? Okay, so the other thing is that since we know what state we're trying to get, so the way I've done it this way, we're always going to keep the output state. But if we're really worried about having a high error rate on our magnetic states, we can do even better by just trying to identify if there's errors and throwing them out if there are. Okay? So in particular, this is a distance 3 code. So it can correct one error, but it can detect 2 errors. So if instead of doing error correction here, we do error detection, and we say, if we don't see any errors, we'll keep it. If we do see errors, we'll throw it away. Well, what happens then? Well, then if there's 1 error, we'll detect it, throw it away. If there's 2 errors, we'll detect it and throw it away. And so it's only if there's 3 errors do we actually have a problem. If there's no errors, well, we'll see that there's no error. Well, we won't notice any errors, and so we'll keep it. And if there's 3 errors, it's possible we also won't notice that there's errors and keep it. And so in that case, we only get a problem when there's 3 errors, which is order p cubed. Okay? So we can reduce the error rate even further. But it's a trade-off, because the problem is that when there's 1 error, and we do error correction, we get to keep the state. Whereas in this case, if there's 1 error and we do error detection, we throw the state away. Okay? So while with error detection, we can reduce the error rate more quickly, it's less efficient in terms of things used. In this case, we always get 1 magnetic state out. In the other case, we only get it some of the time. Okay? Okay, so are there questions on this magnetic state distillation? Yeah?
So this particular code doesn't have all the cliff-or gates as transfer.
That's correct, yeah.
So if you want to use this magic state and use it for a code which has transversal cliff-or gates, can you
Yeah, so again, I want to just think of this, forget about for the moment about the fault-tolerant protocol as a whole. I just want to focus on this magnetic state distillation procedure. Once we understand that, then I'll go back to talking about the fault tolerance. But the main point is that this code is completely separate from the one that's going to get used in the fault-tolerant protocol.
can you still supply this magic state to a different code?
Yeah, I'll explain how to do that in a minute. Yeah.
Can you comment on the decoding?
The decoding, yeah, sure. So the error correction procedure involves measurement of the stabilizer generators. You can use, say, the Steen error correction procedure. You don't really have to be fault tolerant, actually. It doesn't have to be. Could just be a simple. Also, there's lots of ways to do it, but in particular, it only uses Clifford group gates because this is a stabilizer code. And similarly for this decoding procedure, it's just the inverse of the encoding procedure, which is also Clifford group. No. Remember, because we're in this model here, which maybe you can't see from there. We're assuming perfect Clifford group gates. Okay? So anything with Clifford group gates in here is perfect, and it's only these pi over 8 gates that we have to worry about having errors. Yeah?
When you detect a single error,
Mm-hmm.
then why are you throwing it? Because we can anyway correct it.
Well, yeah, so that's the thing, is that you can either operate this as an error correcting code, in which case when we get a 1-qubit error, we can identify what it is and correct it, or we can operate as an error detecting code, which allows us to detect 2 errors, but then we give up the ability to correct 1 error. So the reason for that is because there will be some single-qubit errors that have the same error syndrome as 2-qubit errors. Maybe it's the other way around. There's some 2-qubit errors that have the same error syndrome as 1-qubit errors. Okay? And so we can see that both of those error syndromes are not 0. So we know that there's been an error, but we don't know which of the 2 we have. Okay? And so if we were to try to, if we saw that error syndrome, we tried to correct it as for 1-qubit error, but it was actually a 2-qubit error, then we'd create a logical error. That's the important thing. Yeah?
Can you also comment on how to construct this like a 1513 code, or actually what's the underlying idea that they can have a transversal?
Yeah, so it's I did say that actually. So it's a CSS code. So and it's a superposition. The logical 0 is a superposition of things that have weight 0 mod 8, and the logical 1 is a superposition of things that have weight 7 mod 8. Okay, other questions? Okay, so yeah, okay, so let's think about how to integrate this into our fault-tolerant protocol. So let's again, forget about this. Well, okay, so in the real fault-tolerant protocol, of course, we don't have perfect Clifford group gates. We just have fault-tolerant Clifford group gates. But let's ignore that for the moment. Let's assume that we do have perfect logical Clifford group gates in our fault-tolerant protocol. And again, our goal is to just make the magic states better. So how do we do that? Well, so the main thing is, so we can, if we make each of these lines here a thick line in my old notation. So for instance, if we're using a fault-tolerant protocol involving the 7-qubit code, each of the lines in this circuit here is going to be a block of the 7-qubit code. Okay? And what that means is that we're making what's called a concatenated code. Right? We have a 7-qubit code, and then we have the 15-qubit code, and each of the physical qubits of the 15-qubit code is actually the logical qubit of a 7-qubit code. So altogether, we have, well, it's 105 qubits down here and 105 qubits up here. Although we don't actually need to encode the thing up here, really. It's just simpler to write it that way. Maybe, okay? So that's a lot of qubits, but then we have both the 7-qubit code and the 15-qubit code, okay? And we can do, say, Clifford group gates transversally on the 7-qubit code. And remember, we're pretending for the moment that those are perfect. So we can do all of these Clifford group things as gadgets of the 7-qubit code, and those are fine. And then for these things, these pi/8 gates, we do them by magic state injection into the 7-qubit code. Each of these single physical pi/8s is actually a logical pi/8 for the 7-qubit code. Okay? And so how do we do that? Well, we make a non-fault-tolerant magic state for the 7-qubit code and use it to perform magic state injection using logical Bell measurement logical Clifford group gates. Okay? And so once we've done that, we've done this whole circuit at the logical level for the 7-qubit code. Okay? And so then when we decode here, we're decoding only the 15-qubit code, and we get back single blocks of the 7-qubit code. And so we get a magic state encoded in the 7-qubit code, and it has this lower error probability. Okay? Now in reality, of course, these Clifford group gates are not perfect. But because they're logical gates of the 7-qubit code and they're done fault-tolerantly, you can also think of their error rate as being like order p squared. Okay, if there's a p error per gate, per physical gate. Really physical gate in this case. Okay, so that means that the whole error rate of this whole thing is O of p squared, which is our real goal all along. Okay. Now in practice, it's often done with codes that are much bigger and much better at correcting errors, concatenated codes or the surface code, in which case the logical error rates of all these Clifford group gates will be much, much lower than O of p squared. And in that case, the magic states that we get out are probably not good enough for us. Okay? And because if we want to reduce the error rate from p to O of p to the 24th or something, getting the magic states that are down to O of p squared is still going to totally dominate our errors, way higher than we want. But we can do magic state distillation more than once. Okay? So if we start out with 15 magic states and do this procedure, we get the error rate from 15 order p magic states down to 1 order p squared magic state. Then suppose we take 15 of these p squared error magic states and do it again. What do we have now? We have something that's O of p to the fourth. So we get p to p squared to p to the fourth. We can do it again to p to the eighth, and so on. Okay? And of course, each time we're doing this, we're blowing up the number of magic states that we need by a factor of 15. So that's a pain in the neck. But you can see it goes down very quickly. And so we're not going to have to do this very many times. So I'm going to do that counting again when we talk about the threshold theorem in a little bit. So I'm not going to go through the full calculation here. But it turns out that the overhead is kind of reasonable. Reasonable in the theoretical asymptotic sense. But in practice, it turns out to be very big numbers. Now, I should say that this 15-qubit distillation procedure is not the only one known. It's probably not the most efficient one. But I like to bring it up because it's kind of conceptually the most clear. OK? So are there any questions on magic state distillation? Yeah.
Explain again why we are using the 7-qubit code inside this 15-qubit code.
Yeah. So now I want to integrate this into a fault-tolerant protocol. So for the 7-qubit code, that's going to be the main code we're using for the fault-tolerant protocol. And for that, we know how to do everything except for the pi over 8 gate, basically. And so this thing, this distillation procedure here, it's only for making the pi over 8 magic state better. Okay? And you could also say, well, why don't we just use this 15-qubit code to start with? Right? And then you'd have the transversal pi over 8. You wouldn't have to do this distillation procedure. But then you wouldn't have the logical Hadamard gate. Okay? And you'd have to do some sort of similar distillation procedure for the Hadamard gate. And moreover, the 15-qubit code is less good at correcting errors than the 7-qubit code because it uses more qubits to accomplish the same amount of error correction. Now, people have come up with various kinds of alternative strategies like switching between codes. You start, maybe you use the 7-qubit code most of the time, but then when you want to do a pi over 8 gate, you switch it to the 15-qubit code. That's, you know, you have to, there's lots of different things you can do. People have come up with, actually by now, a wide variety of techniques to avoid this magic state distillation. None of them are clearly better when you take in everything into account, like what code do you have to use? Is it a really good code or a bad code? What are the actual amount of resources that you need to do this procedure? Stuff like that. In some regimes, some of these procedures seem to be better. In other regimes, they're worse. But there's a whole range of protocols by now out there. So I'm not going to have time to go through really anything else. But this is kind of the main one that's used.
And you also said that it's 15 choose to p squared. So
yeah.
That
Well, right. It might actually be less than that because the so the point is if there's two errors, that'll cause a problem when we're doing the error correction. And so in the worst case, it could be any pair of qubits that would cause a problem. And then there's 15 to choose two pairs. So that 15 choose two pairs times p squared for any given pair, that's where I got that number. But it could be that some pairs are actually OK, that you can detect them. So it could be less than that. Any other questions? OK, so that completes the fault-tolerant protocol. I've shown you kind of all the components necessary to get a universal set of gates, measurement preparation. So now you can take any circuit, that ideal circuit that's given to you that you want to implement, provided it's broken up into these appropriate gate set, and then transform it into a fault-tolerant circuit using the gadgets that we've seen. But there's kind of at least one missing piece of proof here, which is how do you know that this actually works to improve the error rate on the circuit as a whole? And this is where these diagrams that I was drawing for these definitions pay off, because there's a relatively straightforward proof of that from what we've done so far. So let's see here. So remember, we have this procedure that's going to take a circuit, and we have some gates. Well, I guess we should start with state preparation. And then after each location, we stick in, so each location we transform into a fault-tolerant location. Then we stick in error correction after that, and maybe do some measurements. So this is kind of, at a schematic level, what our fault-tolerant circuit will look like, right? It's a sequence of gadgets. Preparation gadgets, measurement error correction gadgets, gate gadgets, and measurement gadgets. And so to analyze this, I want to, okay, this is where I need two colors. So to analyze this, I want to break it up into smaller components, rather than try to analyze it all in one chunk. So what I'm going to do is I'm going to look at what's called extended rectangles. Or XREC. So it's a preparation gate or measurement gadget plus the error correction gadgets before and after. So these are kind of the state preparation XRECs. And then the gate XREC, you see, looks like this. So this error correction, gate, error correction, and these error corrections, gate, error correction, these are gate XRECs. And then we have measurement XRECs at the end here. So I mean, it's hard to probably see all the separate green dotted lines, but if you followed what I was drawing or saying, you can see that these XRECs here overlap with the XRECs that are adjacent to them in the circuit, right? Because they share the error correction procedure. The error correction gadget that's after one location is the one that's before the next location. Okay. So what we're going to do is we're going to look at these. Oh yeah, and so this 2 qubit gate, this 2 block gate, its location has both of these blocks, code blocks in them, both of these logical qubits, and so it has 4 XRECs in it rather than 2. 4 error correction gadgets in it rather than 2. Okay. And so what we're going to do is we're going to look at each of the extended rectangles in isolation and try to analyze it, whether it's doing the right thing or not. Okay? So if we have a code that corrects T errors for this protocol, we say that an XREC is good if it contains less than or equal to t false. Otherwise, it is bad. Okay? So the idea here is that if any of these xrecs has lots of faults in it, well, that's an accumulation of lots of errors. We don't expect our code to be able to deal with it. But if the number of faults is low, then our code should be able to correct those errors, right? And so we expect, in that case, for the extended rectangle, for the gadget inside the extended rectangle to do what we want it to do. Okay? Does that make sense? Okay. So so what does it mean? What we want it to do? So we say an xrec is correct if the following equation holds. So I'm just going to draw this for the gate xrec, but you can come up with something similar for the preparation and measurement xrecs. And I'm actually just going to draw it for a single block gate xrec. So here's the xrec, and suppose we follow it with an ideal decoder, right? So we're asking, what is the logical state after this xrec? Well, for it to be correct, that's saying that it should be basically the state that went into the xrec and then followed by the ideal gate. Okay? So so let's see. So what I've done is I'm saying that it's correct if we can push this ideal decoder back through the gate. But notice that I don't push it all the way back through the xrec. I only push it back until after this error correction step. And the reason for that is that this thing here is not making any reference. There's no filters in it, right? So it's not making any reference to the number of errors that come in. That's why we want this error correction step here, to get rid of any pre-existing errors that might have been in the input state. Okay? And that's also the reason that we defined these xrecs to include the error correction steps both before and after. We want them after to get rid of any new errors that might have occurred during the xrec, and we want them before in order to get rid of errors coming into it. Now, of course, this one could have some errors. This error correction step could have some errors coming into it, but that's still within the xrec, so there's not going to be too many of them, assuming it's a good xrec. Okay? And so hopefully the arguments that I've made so far have primed you to believe this theorem statement. A good xrec is correct. Right? So I'm saying that if you have an extended rectangle that has less than or equal to t faults in it, it behaves in this way. The gate gadget does the logical gate. Okay? And we can prove this by pushing around these diagrams that I have drawn on the upper left board there. So let me do a little bit of that. Okay? So so let's start with the left-hand side here. Okay, so first we have at most t faults altogether in this xrec. But we're going to have to break that down into faults in different parts of it, the three different gadgets. So let's say there's S1, S2, and S3 here. Okay? And we have that S1 plus S2 plus S3 is less than or equal to t. Okay, now to push this ideal decoder back, we want to use some of our correctness properties from over on the left. But if you look at all the correctness properties, they have filters in front of them. Okay, and we have no filter here. So we have to create the filter somehow. And if you look at these properties, the only one that can kind of create a filter without having one there is the ECRP. Okay, and so we can apply the ECRP. Well, we could apply it here, but that's not going to help us because we don't want to filter here. We want to filter here. So we're going to apply it to this one. And so that gives us this. So this had S1 faults, and so the ECRP says we have S1. We can stick in an S1 filter here. Okay? And then we have a filter and then a gate gadget. So now we can apply the gate propagation property to move to add a filter here. And so this is an S1 plus S2 filter because we have the pre-existing errors plus the errors in the gadget. Now we have EC and then ideal decoder. Okay, so now we have filter, error correction, ideal decoder. So now we can apply the ECCP, the error correction correctness property, to push this ideal decoder through the error correction. Okay, so we've gotten rid of this trailing error correction step. So now we would like to push the ideal decoder back through this gate gadget. So we can do that using the gate correctness property up there, right? But let's look at the gate correctness property. It says filter, gate gadget, ideal decoder. And that's not what we have. We have filter, gate gadget, filter, ideal decoder. So we have to get rid of that filter. Well, how can we do that? And the way we can do that is using this gate propagation property in reverse. Right? It's an equality. Before we use it to go from the left-hand side to the right-hand side, but it's equally valid to go from the right-hand side to the left-hand side. And that's what we have here. We have filter, gate, filter. So we can get rid of the second filter. And so once we've done that, we have what we need to apply the gate correctness property. Okay, and now we're almost where we want to be, but again, we have to get rid of this filter. And we can do that by applying the ECRP in reverse. Okay, and that's what we wanted to get. Okay. So again, the intuition here is that if there's not too many errors anywhere or total cumulative in this XREC, then the logical gate here is the correct logical gate. Okay. And so we have, I mean, I didn't call it out explicitly, but we have been using this property at every step along the way, right? Because all of those correctness and propagation properties were dependent on the total number of errors being limited to t. And so in particular, at this step, we needed all the sum, s1 plus s2 plus s3, to be less than or equal to t. And that's just saying that, well, if we don't have that, then errors could accumulate from the end of this error correction step and in this gate gadget and the beginning of this error correction step to be too many for us. They would overwhelm the code. We wouldn't be able to correct them anymore. Okay? And so that's why we need the sum of all of these things, the errors in all of these things, to be less than t, less than or equal to t. Okay? Are there questions on that? Okay, so if you want some practice on this, here's an exercise. So do this, by which I mean define correctness and show that good implies correct for preparation and measurement XREX. They're pretty similar. Okay? Okay, so now we can analyze each XREC by itself. Actually, I think I may do the definition of correctness for the preparation and measurement in what I'm about to do. So you only have to do the proof. Okay, so now let's look at a circuit like a complete circuit, okay, and see what happens to it. So we're going to have a circuit. I'm going to take a very simple circuit, just for example. So we're going to prepare a state, do error correction. We're going to do a gate, do error correction, and then we're going to measure it. Okay, and this is broken up into XRECs. Okay, and I claim that if all of these XRECs are good, in a circuit are good, the circuit is then equivalent to an ideal unencoded circuit. Okay? So that's kind of well, it's not quite the end goal of fault tolerance, but you see that we're getting close, right? We want this encoded fault-tolerant circuit to, even in the case where there's some errors, it will give us the correct answer to our computation. Okay, so how do we prove this? Well, it's again one of these diagram pushing exercises. So, so we start with this thing. And now we're going to apply the correctness properties over and over again. Since each of these XRECs is good, we can do that. So we're going to start with this last XREC. So this is where I have to implicitly write down what it means for a measurement XREC to be correct. And it's kind of the same idea. There's no trailing error correction here. So what we're going to do is we can create an ideal decoder here and stick in an ideal measurement at the end. Okay? So again, the spirit of correctness is that we can replace the fault-tolerant gadgets with ideal gadgets when the XREC is good. Okay? And now we have this XREC, which is a gate XREC, and it's followed by an ideal decoder. So that's exactly the situation where the gate correctness property holds. And so we push back the decoder further. Okay? And now we have a state preparation error correction. So this is a state preparation XREC followed by an ideal decoder. And so we're going to apply the state preparation correctness property, which is going to kind of eat up the ideal decoder because there's nowhere to push it back to, but it leaves behind an ideal preparation. And so you see, this is what I claim, that the encoded circuit, when all XRECs are good, is equivalent to an ideal circuit. There's no errors here at all, remember. But in here, there are some errors. There's not too high a density of errors. There's at most t on any XREC. But there are errors, and it's equivalent to a circuit that has no errors at all. Okay? Okay. So so now I want to ask the question, what happens if an XREC is bad? What happens if we have a big circuit? I mean, if we have a really big circuit, it's unreasonable to expect that every XREC will be perfect, will be good, sorry. Right? If t is equal to 1, so like we're using the 7-qubit code, then, well, the probability of having one error in an XREC is order p. But the probability of having two errors in an XREC, two faults, which is enough to mean that this proposition doesn't apply, the probability is order p squared, right? So if the error rate is order p, you can only do about 1 over p gates before you're likely to get an error. And so we've definitely improved on that. We can do about order 1 over p squared before we're likely to get an error. But sooner or later, we will get an error. Okay? So how do we deal with that? So I'd like to make a more general statement that this fault tolerance is still working to some extent, even when some of the XRECs are bad. And unfortunately, to prove everything here requires some additional machinery, and things actually get fairly complicated. So I'm not going to do that. But I'm going to make a claim which probably will be reasonably obvious to you. It's just actually proving the claim can be difficult, which is that if you have a bad XREC, it acts like an unencoded gate but with an error on it. Okay? And so when we do this whole thing of creating the ideal decoders and pushing them back through, it has to be modified slightly to make this work. What we're left with is a circuit that looks like this, but whenever we had a good XREC, we have a correct decoded gate here. And whenever we had a bad XREC, we have a gate with an error in it. Okay? So this is called level reduction. So each good XREC creates a gate that has no error. each bad XREC creates the gates that had an error. And we have bad XRECs with probability O of p squared. So our encoded circuit is then equivalent to an unencoded circuit with an error probability that's O of p squared per gate. Okay. Now there's a catch here, which is that even if the original physical error model was one of these independent stochastic models where the error per gate was totally independent of the errors in the other gates, that's not the case after level reduction. And the reason it's not the case is because these XRECs overlap. Right? So if we have, like over here. So like this XREC overlaps with this XREC. And suppose we just happen to get a lot of errors in this error correction procedure. Well, that, the way I phrased it, will make both of these XRECs bad. Okay? And actually, that's a problem, because that means that we would then have a correlated error model where a single concentration of faults can cause 2 errors in the unencoded thing. So we'd have, this O of p squared event happens, but now it causes 2 gates to go bad, or 2 locations. So this is why this argument gets a bit complicated. It turns out that what you can do is you can kind of shuffle things around so that in that particular case, this measurement has an error, but this gate does not, unless there's more errors over here. Okay, so we can make it so that it's kind of independent to have a probability of error per gate, but it's not totally independent. There's a little bit of correlation, but it's kind of manageable correlation. Yeah.
So all that we had done before were done accounting to the independent errors, right?
Yes, sort of. That was the model that we were working with. But actually, basically everything I was doing was just saying, suppose we just happen to have this many faults in a gadget or in an XREC,
So even if
without a really statement about where those faults came from.
So even if our errors are correlated, we can still use this properties and theorems, and then we can again reduce to P4s and etc., right?
Yeah, so it's only when we start to talk about error probabilities that you have to worry about those correlations. Okay? Now, in the magnetic state distillation, it really didn't come up at all, because what I care about is correlations between totally separate procedures, right? Making one magnetic state versus a separate magnetic state. Okay? So, none of this procedure will introduce correlations between those two things. It's only between adjacent gates that we're worried about, really. And here, it turns out that the correlation is, if you treat everything correctly, the correlation is completely under control. There is a correlation, and so the biggest problem that you'll get is trying to state exactly what you mean. And I could do that, but it's, I think, not sufficiently critical to do it, since we don't have too much time left. Okay? So let's just take for granted that there's a little bit of correlation here. And in fact, there can be fairly strong correlation in the type of errors that you get as well. But it's really the probability of having errors on one place versus another that's the most important. And that is under control. Okay? Yeah?
Is this order p-squared error probability only for distance 1 code, or distance 3 code, or for arbitrary distance code?
Yeah, you're right. This is for a distance 3 code. So if you have, if you use the fault-tolerant gadgets in the way I've said, that have these properties, and you have a code that has higher t, then this is O of p to the t plus 1, right? Because we have a problem whenever we have more than t errors in an XREC. So actually, let's look at this a little bit more. So I said O of p squared. So what is that constant there? So it's kind of the same argument I was making up here with 15 choose 2. We have this X rec. It has many locations in it, and potentially, if any two of them go wrong, well, if any two of them go wrong, that means the X rec is bad, right? And that might be equivalent to an error. Now, of course, it's true that not all pairs of locations are going to cause a problem, but at this level of precision, we're not going to worry about that. We're going to say that any pair of locations could cause a problem. So how many pairs of locations are there? Well, if there's A locations in the X rec, then there's A choose 2 pairs of locations. And so the effective error probability is then A choose 2 p squared. And this is really just an upper bound, right? Because, like I said, there's some pairs that might not cause an error. And this is actually not exactly p squared, right? Because you have to say, what's the probability of having exactly 2 errors? Well, it's at these locations. It's p squared times 1 minus p to the a minus 2. And then you have to add up the 3 errors and the 4 errors and so on. So this is just an upper bound. And while we're doing upper bounds, we might as well let A be the locations in the largest X rec. And given the gate sets that I've shown you, that's generally going to be the C naught X rec. Depends exactly how you count the magic state distillation. But OK? OK, so now we have a fault-tolerant procedure. And so you'll notice that when P is kind of not that small, this could be larger, right? When P is small, this is definitely better. When P is very small, this is definitely better than the original P. P prime is an improvement. But when P is kind of large, it might not be, right? And the reason for that is because, well, we added a lot of locations. We started with one location for our gadget. We added many, many extra locations for error correction, for the extra qubits involved, and so on. And so those extra locations have more possibilities for errors occurring, right? And so fault tolerance and error correction more generally is kind of a race between the extra errors that we're creating by adding these extra locations and extra gates and our ability to correct them. And if the error rate is kind of moderately high, then we can't keep up. The extra qubits and the extra locations will have more errors than we can handle. But if the error rate is low, then we get ahead, okay? And we're able to actually reduce the error rate by using this fault-tolerant circuit. Okay? So you might reasonably ask, so we have this encoding procedure that takes some unencoded circuit with error rate p per location and turns it into an encoded circuit with, when p is small, a lower error rate per location. An encoded circuit that's equivalent to a circuit with a lower error rate per location. If we've done that once, why not do it again to make the error rate even lower? And you can do that. So that's called a concatenated code. And using it, we can say, well, if we can reduce the error rate once and we can reduce it again, why not reduce it even further and further and further and further? And so that gives us the threshold theorem. And so the threshold theorem says that if p is less than some threshold value, then there exists fault-tolerant protocols for arbitrary circuits and I'm going to say the size of this circuit, number of locations, is big T. such that the logical error rate is epsilon, which you can choose arbitrarily, and the overhead, so the overhead could be in a couple of things. So it's the ratio of physical qubits to qubits in the original circuit, or it could be the ratio of the number of locations in the encoded circuit versus the original circuit, or the time, the number of the depth of the computation. And the overhead is some polynomial in the log of t over epsilon. Okay. So this is saying that as the computation you want to simulate with the fault-tolerant circuit gets larger, you have to do more error correction, and therefore you have more overhead. But the rate that it increases is very slow with the size of the circuit you want to simulate. Obviously, the original circuit is getting bigger, so you need more qubits for that. But the ratio of extra qubits that you need for fault tolerance is not so much, or at least it doesn't increase so rapidly. If you look at kind of real protocols that are out there, most of them do have fairly large constants here, like 100 or 1,000 or something like that. So you do actually get a pretty big blow up in terms of the size of the computation. But the advantage of this theorem is it says that if you wanted to go in much, much longer computations, you don't need much, much more error correction. The error correction only increases slowly with the size of the computation. Okay, so let me quickly prove this threshold theorem, since we've done most of it already. And and basically, it's just what I said, that you have a question? Yeah, so the overhead, I mean, it's the ratio of kind of physical resources to logical resources. Okay, so if you want to think just qubits, physical qubits over logical qubits. But it could also be the number of physical gates, say, over the logical gates. Okay, the logical gates are the ones in the original circuit that you want to simulate. Okay, so what's the proof? Well, what we're going to do is we're going to imagine using a concatenated code where we take our original circuit, we encode it using, say, the 7-qubit code fault-tolerant protocol, and we do this again and again and again until we get the logical error rate down as far as we like. And then we're going to invoke level reduction many times. So let's say we have L levels of encoding. Well, so if we started with we have some big circuit involving these L levels of encoding, and the physical error rate on that is P. Okay? And suppose we take off the last level of encoding. Well, level reduction tells us it's equivalent to a circuit that doesn't have that encoding, so it only has L minus 1 levels of encoding, and has an error rate P prime that's at most really h choose 2 p squared. Okay. Now I want to rewrite this. I'm going to say that. So I'm going to define p sub t, which is going to become the threshold, as 1 over h choose 2, and then p prime over p sub t is equal to. So this is p squared over p sub t, but then we've divided again by p sub t, so we get p over p sub t squared. Okay? And so this is going to be much more easy to do a recursive thing on. So when we do that, so then we take off another level of encoding. We'll find that p prime goes to p double prime. And P double prime over P sub t just follows the same equation. It's P prime over P sub t squared, right? Which is P over P sub t to the fourth. And you can see that every time we do this, we're going to square this again. So in other words, after removing L levels of encoding, we're going to get an effective error rate that's P over P sub t to the 2 to the L. So you see that this is going to go to very, very small very, very rapidly, right? It's a double exponential. Now, what about the overhead? What is the actual overhead we need? Well, the 7-qubit code, if we have L levels of encoding, every time we encode, we blow up by a factor of 7. It's actually bigger than a factor of 7 because all of these fault-tolerant procedures used a bunch of ancillas. But the number of ancillas is just some constant, right, for each level of encoding, for each gadget. So, so the overhead is some constant to the L. Now that looks bad. That's an exponential. But the error rate is decreasing as a double exponential. So compared to that, a single exponential is like nothing. So when we put this all together, we see that if we want P sub L to be epsilon, then that implies that we want L to be something like, well, okay. So yeah, so I was a little bit careless on this. So this is where the t is going to come in. So this is the error rate for the whole circuit. So so to get an error rate for the whole circuit that's epsilon, we want the error rate per location to be epsilon over t. Okay? And this is decreasing when p is less than p sub t. This is decreasing as a double exponential. And so we need L to be like log t over epsilon to get that. Okay? And then the overhead, c sub L, c to the L, is what I said, a polynomial in the log of t over epsilon. Okay? So that's the threshold theorem. Are there any questions on that? Okay, so the threshold theorem is kind of the central result of the theory of fault tolerance. Concatenated codes are not the only way to prove it. You can also get a threshold from other families of codes, most notably the surface codes, which are very popular candidates for actually implementing real quantum computers. John Martinez talked about those yesterday. So surface codes also have a threshold as you get to larger and larger surfaces. But it behaves qualitatively the same way, where you have polynomial polylog overhead. That's kind of saying how big you need to make the surface in order to get a certain amount of error suppression. And the threshold theorem is really kind of the key enabling result for building a quantum computer, right? Because without it, you'd say, well, in order to make bigger and bigger quantum computers, we need to get the physical error rates down lower and lower and lower. And that would be really hard. The threshold theorem says no. You only have to get the error rates down low enough. And once you've done that, we can apply these fault-tolerant protocols in order to make arbitrarily large quantum computers. Now, there's a cost. You need extra qubits. You need extra gates. At least asymptotically, that cost is not too large. But it is a big cost in practice. And so I think one very interesting avenue of research is to try to come up with protocols that use less overhead, but still can work at reasonable error rates. So you're probably interested in what the actual numerical value of the threshold is. Now, I want to put in a lot of caution when I give these numbers because there's a lot of assumptions that go into all of this. And I'll discuss those in a minute. But for this concatenated 7-qubit code, we can prove that the threshold is at least 2.7 times 10 to the minus 5. When you use the error models that I've been talking about so far. Now, it's probably a little bit higher than that. This is a proof, so you have to make conservative assumptions. Now, if you go on the other way and say, well, if you simulate fault-tolerant protocols and try to figure out what the error rate, and you look at all sorts of different protocols, the best record is a protocol due to Manny-Nil, and simulations there suggest the threshold might be as high as 5%. Again, depending on assumptions. Okay. Now, these numbers are not directly comparable because one of them is a lower bound as a proof. The other is an estimate via simulations. The other thing is that this number is coming from kind of worst case error models. This is done for the depolarizing channel where all errors are equally likely. And of course, real error models are much more complicated than either of those. But this kind of gives you the range of possibilities. Now, this particular protocol, while it still has polylog overhead, the actual constants are ludicrous. I mean, they're like billions or more. Okay? So this is not a protocol you'd actually want to run in practice. But it gives you an idea of kind of what you might achieve with the best possible protocols. Surface codes seem to have a threshold that's about 0.7%. Yeah?
Can you remind me, are there any proofs of threshold for surface code, or it's all based on simulation?
Certainly the 0.7% or thereabouts that you see is 100% simulation. No, actually that's not true. It's about 90% simulation and 10% hand waving. So the hand waving comes in because as long as you're doing a circuit that just consists of Clifford group gates and Pauli errors, you can do that with a simulation, right? An efficient classical simulation. But once you want to throw in magic states, that's a non-Clifford group operation, and now your simulation breaks down. You don't have an efficient algorithm anymore. Okay? And so you have to do some hand waving to say, well, probably it's not going to change the threshold too much. So that's one reason why I personally like to stick with proofs. I'm not totally sure what the status is of proofs for the surface code. Austin Fowler has claimed to me to have one. I haven't gone through it to see if I believe it or not. So maybe. But I definitely don't know what number he would get out of that because I didn't look at it closely. Yeah.
So over there you said that PT is 1 over A choose 2. That's different from those estimates over there.
Yeah, it is. So, well, first of all, I didn't tell you at all what A was. If you do this for the 7-qubit code with the A choose 2, you get like 10 to the minus 6 or so. So this better number comes from more careful counting of errors. Remember I said that not all pairs of locations are actually going to cause correctness to fail. Actually can cause a problem. So if you're more careful about how you count those, you can incorporate that into the proof and get a number like this.
And what is A about? Or how do you figure
I don't remember offhand. Probably 10.
What are you counting again?
So you're counting. So it's set by the C0 XREC. Do I have one somewhere? So you have the size. It's basically 4 times the size of one of these EC circuits plus 7 for the transversal C0 gate. Okay, so it's a fairly big number, but yeah, you can get it down a little bit by being more careful about the counting. Okay, so let me very quickly then say something about the assumptions that go into this threshold theorem and to what extent they're needed. So one assumption is locality. So all of the circuits that I've shown you, I mean, they all involved 1 and 2 qubit gates, but I wasn't at all careful about where the qubits were located relative to each other, right? And particularly when you start to do concatenation, you get these very big codes, and you might have to interact a qubit with one block to a qubit in a different block, which you might have to store very far away. Now, even in concatenated codes, you can get around this. You can be a little more careful about how you place everything. And with the big blocks, they do have to go far away, but you don't have to do that very often. And so if you're careful about doing that, you can find that you still get a threshold even when you're restricted to nearest neighbor gates in 2 dimensions or even 1 dimension. Okay? But the threshold might be worse. Now, as it turns out, the surface codes sit very naturally in 2 dimensions. And so they're a very good candidate if you're restricted to nearest neighbor gates in 2 dimensions, because you don't kind of lose anything for going to 2 dimensions. It's already incorporated into that threshold that I mentioned. Now, if you're stuck in 1 dimension, then all bets are off. You'll have to work harder. There is still a threshold again, but it is probably going to be lower. So let's see, what else? So at various stages, I assume that we could make measurements in the middle of the computation and then do stuff based on the measurements. For instance, error correction. You measure the error syndrome, and then you correct based on that error syndrome. State injection, magic state injection. You measure, and then you do some Clifford group operation depending on the outcome of that measurement result. So in a lot of implementations, that's kind of inconvenient. Measurements might be slow or even hard to do in the middle of the computation. Maybe you can only do them at the end. So again, this is something that's not really necessary, but it is pretty desirable. So in principle, all of that classical computation that you do after the measurement could be done using qubits, right? So you can eliminate the measurement altogether, do all the classical control using qubits. But the problem is the qubits are susceptible to error, whereas we're assuming the classical computation is not. And so you have to encode that classical computation using a fault-tolerant protocol as well. Now, you don't want to do a quantum fault-tolerant protocol because that would require more classical computation and so on. But luckily, there's a very simple classical fault-tolerant procedure, which is just the repetition code. You take everything and repeat it multiple times, and occasionally take the majority to check. Okay? So using that, you can kind of eliminate the need for measurement altogether, eliminate the internal classical computation. But again, there should be some cost in terms of the threshold. You'll still get a threshold, but it won't be as good. If measurements are merely slow, probably you can deal with that in other ways. You can basically have your computation wait around. Well, so if it's just the error correction measurement, you kind of put off doing the error correction until you need a non-Clifford group gate. You can track Pauli errors through Clifford group gates. And then when you want to do a non-Clifford group gate, say with magic state injection, now you have to wait around. But you have a lot of error correction capability, so you can probably do that. Let's see. So what about the error model? So in what I've done here, I'm assuming a stochastic error model, where errors occur with some probability per location. Now, as I said, we can tolerate a little bit of correlation. And so like 2-qubit correlation, well, okay, so the main thing is you want the probability of errors on many qubits to fall off exponentially with a number of qubits. So if you have like 2-qubit correlated errors, that still satisfies the condition. But it's still kind of a problem. You still have a threshold, but if you have 2 errors occurring at a time, then, well, a code that corrects only 1 error is probably not going to be good enough. You might need a code that corrects 2 errors. Okay? And this has not really been fully studied, what it does to the thresholds, but it's definitely something to be concerned about. Now, if you have 2-qubit or 3-qubit errors, you will still have a threshold. But if you have many qubit errors, then that's a much bigger problem. You can't really hope to correct for an error that affects all the qubits in the computer at once. For instance, if a meteor comes down and strikes your computer, destroying the whole thing, you can't expect error correction to save you from that. Maybe a more realistic concern would be a power failure. Okay? But of course, the same thing is true of a classical computer, right? I don't think they make too many meteor-proof classical computers either. So in the real world, these highly correlated errors do happen, but they're very, very rare, enough that we're pretty comfortable ignoring them. And I think the same could be true of quantum computers. But it's still a potential concern. And so the other aspect of this error model is it assumes the errors are probabilistic. I guess John Martinez mentioned this as well, that if you have coherent errors, they can build up much more quickly, right? Because if you have a rotation by an angle theta, and you do that again and again, well, an angle theta, the probability of error, if you do it just once, the probability of error is order theta squared. But if you do an angle 2 theta or 3 theta, the probability of error is now 4 theta squared or 9 theta squared. So it's building up quadratically. In that case, you will still get a threshold, but if you follow the proofs, the threshold value will be much, much lower if you kind of compare error probabilities. And that, of course, would be a big concern. Now, I think in practice, this is probably not a big problem because the fault-tolerant protocol doesn't involve doing the same gate over and over again. You're kind of alternating between various different gates. You're mixing in ancillas. It's hard for errors to really build up coherently. But it's at least an open question whether it's going to be a concern or not. If it is a concern, then you need some techniques like what John was talking about with randomized compiling to try to get rid of those coherences. So another class of error models that occur in the real world that are not included in the theorem, as I've stated, is non-Markovian errors, where you have the system interacting with some environment, and the environment has a memory. And so the errors that occur at later times are related to the errors that occurred at earlier times, and related potentially to what you're doing in your computation. So we have a pretty general proof for a wide variety of non-Markovian errors that there is still a threshold. Again, there's this concern about coherent versus incoherent errors, so that could be the threshold is lower. But in principle, we know that for a lot of non-Markovian systems, there will be a threshold. But there's still some non-Markovian errors that are not covered by those theorems. So that's another possible source of concern. OK. So there's a few more assumptions that go into this. We're assuming that gates can be done in parallel. That's really necessary. Otherwise, if you just do one gate and then another gate and then another gate, you won't be able to error correct your whole big computer before the first gates decohere, first qubits decohere. The specific gates that I've told you about here are not essential. You can switch between different universal gate sets, although this particular gate set is good for fault tolerance. So you might want to switch at the physical level from whatever gates you're doing in your real implementation to these. So you need some source of fresh 0 qubits during the computation. You don't want to have qubits sitting around for a long time before you use them for error correction, or they'll go bad. Or at least you need some way of cooling them down again. And the last note I wanted to make was about leakage errors. So I didn't talk at all about leakage errors, where you have, your qubit is actually really, in the real world, part of a much higher dimensional system. And in some cases, you have to worry about it leaking out of your computational space into other states. So again, this is something John Martinez mentioned about tuning the pulse time to minimize leakage errors. But you will still get some leakage errors. And if you don't do anything about them, that will eventually kill your computation, because you can slowly leak out of all your qubits can slowly leak out of your computational space. And if you never return them to the computational space, then you're left with nothing. But luckily, it's not so bad in reality. So there's various ways you can deal with this. You can monitor them and return them to your computational space. Moreover, if you know that a qubit has leaked and you replace it with some random qubit, you don't know what it started as. But now you're not talking about general errors. You're talking about errors in a known location. That's an erasure error. And so that's easier to correct. You have extra information. There's other techniques you use, like the magnetic state injection procedure involved teleporting the qubit from the logical state from one block to a different block with different physical qubits. And so if the qubits in the first block leaked, the qubits in the second block will be fine, or at least their leakage is independent. Okay? So that's another way of kind of restoring you to the computational space without having to worry too much about what actually happened. Okay, so I'm over time, so I better stop there. Thanks.